Hi everybody. In this video we continue with chapter 15, probability distributions, and specifically section 15.4, the normal distribution. So the most important type of a continuous random variable is the normal random variable. The probability density function of a normal random variable x is determined by two parameters, the mean or expected value mu and the standard deviation sigma of the variable. Now you can notice here that the normal probability density function is a bell-shaped density curve that is symmetric about the mean. The variability is measured by the standard deviation, as we can see in these three cases. Now notice that the larger the value of the standard deviation, the more variability there is in the curve. That is, the higher the probability of finding values of the random variable further away from the mean. You can see this in figure 15.22. Now, there's three different normal density functions here with the same mean, but with different standard deviations. Note how the curves flatten as the standard deviation increases. Now, this is because the area under the curve has to stay equal to 1. So in the next slide, you're going to find the probability density function for a normally distributed random variable x. Now, I leave it here, although we will not make direct use of this formula, since it's interesting to note its properties, because they will help us understand how the normal distribution works. Now, the graph of a normal probability distribution is shown in figure 15.23, and notice that the mean or expected value is located at the center of the distribution, and that the distribution is symmetric. Since the total area under the curve is 1, the symmetry of the curve implies that the area to the right of the mean and the area to the left of the mean are equal, and they are both 0.5. Another interesting thing to notice is here in figure 15.24 that one standard deviation to the right or to the left of the mean will mark the point where the curve has an inflection. In other words, where the curvature changes. So in the next slide, you're going to find some information about normal curves, because although there are many normal curves, they all have common properties. Now, one of those common properties is what is known as the empirical rule for the normal distribution. And that is the following. Approximately 68% of the observations fall within one standard deviation of the mean. So that's what we see in figure 15.25 as the orange area. Then we have that approximately 95% of the observations fall within two standard deviations of the mean. We can see that in green here. 95% would be the mean plus 2 standard deviations and minus 2 standard deviations. And finally, about 99.7% of the observations fall within 3 standard deviations of the mean. And that is what we see here in purple. So next we have example 15.19. And it says, heights of young German men between 18 and 19 years of age follow a distribution that is approximately normal, with a mean 181 centimeters and a standard deviation of approximately 8 centimeters. Describe this population of young men. So for this, we're going to use the empirical rule. Now let's remember that in this case, we have that the mean is 181 centimeters and that the standard deviation is approximately 8 centimeters. So this means that 68% of young German men between 18 and 19 would be at 181 plus or minus 8. So that means that they would be between 181 minus 8, which is 173 centimeters, and 189 centimeters. We would also know that 95% would be between 181 plus minus 2 standard deviations, which would be 16. So that means that 95% of those young men would be between 165 centimeters and 197 centimeters. And then finally, we would know that 99.7% of these young men would be between 181 plus or minus 3 times the standard deviation, which in this case would be 24. So that means that it would be between 157 centimeters and 205 centimeters. So next we're going to look at a process called standardizing. The quantity x minus mu tells us how far a value is from the mean. Dividing by sigma then tells us how many standard deviations that distance is equal to. The standardizing process is a transformation of the normal curve. For discussion purposes, assume the mean to be positive. The transformation x minus mu shifts the graph back mu units. So the new center is shifted from mu back mu units. So that means that the new center is 0. The new mean is going to be 0. And also, the standard deviation is going to be 1. Now, if x is a normal random variable with mean mu and standard deviation sigma, the standardized value of x is z, which is equal to this. A standardized value is also called the z-score. So next we have example 15.20, and it says, using the data in example 15.19, work out the z-score of a young German man with a height of 192 centimeters for part A and 175 centimeters for part B. So let's recall that the z-score is equal to the random variable x minus the mean divided by the standard deviation. And in the previous example, we said that the mean was 181 centimeters and the standard deviation is 8 centimeters. So that means that in this case, it's going to be 192 minus 181 divided by 8, and this is going to give us 1.375. So that means 1.375 standard deviations above the mean, because this is positive. Then for B, we would have that the z-score is equal to 175 minus 181 divided by 8, and this is going to give us negative 0.75. So that means 0.75 standard deviations below the mean, since this is negative. Now, what happens if they ask us to find the probability that a normal variable x lies in this interval between 175 and 192 centimeters? Well, we would have to find the area under the normal curve. But there is an infinitely large number of normal curves, one for each mean and standard deviation. So a separate table of areas for each of these curves would obviously not be practical. Instead, what we do is we make use of the GDC. So I'm going to show you how to find the probability that the random variable x lies between 175 and 192 centimeters. So what we do is that we go to second vars, and that takes us to distributions. And we want to pick number 2, which is the normal cumulative distribution function. So the first thing we're going to do is that we're going to find the probability that the random variable x lies between 175 centimeters and 192 centimeters without using standardization. So the first thing you type in is the lower limit which in this case is 175. So we go 175 and then comma. Next we need the upper limit, which is 192. 192. Use a comma to separate that. And next we have the mean, which we said was 181. So 181. And then finally, the standard deviation, which we said was 8. We close parenthesis, you hit enter, and you're going to get that approximately 68.88% of the young men between ages 18 and 19 have a height between 175 and 192 centimeters. Now I'm going to do the same thing, but using the standardization. So if we do that, I mean, it's the same function. We go back to distribution and number 2, the normal cumulative distribution function. So the z-score for the lower value was negative 0.75. So negative 0.75. And then we have the upper limit, which was the high value that we found, and that was 1.375. And then after that, we need the mean, which when it's standardized is going to be 0, and the standard deviation is just going to be 1. And then we click enter, and notice that we get the same value, 68.88%. Okay, so next we have example 15.21. And it says, the age of graduate students in engineering programs throughout the USA is normally distributed with mean 24.5 and a standard deviation of 2.5. A student is chosen at random. Part A, what is the probability that the student is younger than 26 years old? Okay, so for this, we're going to use standardization. Now, the probability that a student is 26 years old means the probability that the student is more than 0 and or equal or less than or equal to 26 years of age. But we're going to use standardization. So for 0, the z-score is going to be 0 minus 24.5 divided by 2.5, and this is going to give us negative 9.8. So that's going to be the lower bound. For 26, the z-score is going to be 26 minus 24.5 divided by 2.5, and this is going to give us 0.6. So we're ready to use the calculator. Notice that, let me turn this on. We would go to second function, vars, and number 2, normal cumulative distribution function. So let's recall that the first thing we type in is going to be the lower bound. So minus 9.8. Separated by a comma, we write the upper bound, which is going to be 0.6. The mean, when it's standardized, it's 0. And then the standard deviation is 1. And we click on enter, and there we go. 72.57%. But for the sake of formality, let's write the answer in terms of z. So we would say the probability of z being less than 0.6 is going to be 0.7257, or like I said, 72.57%. So now let's do part B. For part B, they want us to find what proportion of students are older than 23.7 years. So notice that that means what is the probability that the random variable x is greater than or equal to 23.7 years. Let's turn this into z-score. So notice that here we would have that the z-score for this case is going to be 23.7 minus 24.5 divided by 2.5, and this is going to give us minus 0.32. So what would be the upper bound? Because it's greater than, right? The upper bound is going to be symmetric. Now remember that in the previous case for part A, we found that the lower bound is minus 9.8. So that means that the upper bound, because of the symmetry of the normal distribution, is going to be 9.8. So that means that we can plug the information into the calculator. So let's go to the calculator. And here we go again, second vars, option number 2. And in this case, the lower bound is going to be minus 0.32. The upper bound is going to be 9.8. Then 0 for the mean, and 1 for the standard deviation. And there we are. So that means, in terms of z, right, the probability that z is greater than negative 0.32 is going to be 0.6255 or 62.55%. So now let's do part C. So for part C, they ask, what percentage of students are between 22 and 28 years old? So that means the probability that the random variable x is between 22 and 28. But again, let's standardize this. So the z-score for 22 is going to be 22 minus 24.5 divided by 2.5, and this is going to give us negative 1. The z-score for the upper limit is going to be 28 minus 24.5, this divided by 2.5, and here we're going to get 1.4. So again, let's go to the calculator, and we go to second vars, the normal cumulative distribution function, and in this case, the lower limit is negative 1. Separate this with a comma from the upper bound, which is 1.4. Again, the mean is 0. Standard deviation is 1. Hit enter, and there we are. We get then that the probability that z is between negative 1 and 1.4 is 0.7605 or 76.05%. So now let's take a look at part D, and it says what percentage of age falls within 1 standard deviation, 2 standard deviations, and 3 standard deviations of the mean. So for this, all we have to do is use the empirical rule, because this corresponds with approximately 68%. This would be approximately 95%. And finally, 3 standard deviations from the mean is going to be approximately 99.7%. Now, as an exercise, you could verify this using the normal cumulative distribution function with the GDC. Another type of problem arises when we're given a cumulative probability and would like to find the value in our data that has this cumulative probability. This is what is called the inverse normal distribution. For example, if we need to know what the z-score in the third quartile is, we need to look up 0.75, and the z-score corresponding to quartile 3 is 0.6745. You can see this in figure 15.32. Now, suppose we want to find the z-score that leaves an area of 0.915 below it. The z-score corresponding to 0.915 is 1.3722. We can see that in figure 15.33. Now, let's suppose that we want to find the height of 95% of the young German men between ages 18 and 19. We could use the GDC, a function called inverse norm, and we would find that 95% of these young German men are shorter than 194.16 centimeters. Okay, so next we have example 15.22. And it says, the average time it takes fast trains to travel between London and Paris is 2 hours, 15 minutes, with a standard deviation of 4 minutes. Assume a normal distribution. Part A, what is the probability that a randomly chosen trip will take longer than 2 hours and 20 minutes? Part B, what is the probability that a randomly chosen trip will take less than 2 hours and 10 minutes? Now, there's several ways to approach this, and the reason I'm approaching them simultaneously is because if you notice, both of these times are 5 minutes away from the mean. And that means that these two probabilities should be equal. Now let's suppose this is a normal distribution. So if this is the mean right here, then 5 minutes early would be this area, and 5 minutes late would be this other area. And because of the symmetry of the normal distribution, they should be equal to each other. Now, it's a lot easier to do part B. So first of all, we need the mean. So the mean is 2 hours and 15 minutes. So notice that that's the same as saying 2.25 hours. And the standard deviation is 4 minutes, but we have to convert that to hours. So dividing 4 by 60, it's going to be 0.0667 hours. So we said we're going to do B first because it's easier to find the normal cumulative distribution function from left to right because we can start with 0 and end at 2 hours and 10 minutes. So let's do B first. So notice that 2 hours and 10 minutes is going to be 2.167 hours. So if we go to the GDC, we go to vars again, second vars, and number 2, the normal cumulative distribution function. And in this case, the lower bound is going to be 0. The upper bound is going to be 2.167. Then we need the mean, which we said is 2.25. And the standard deviation, 0.0667. So we hit enter, and there we are. So notice, let's write it with formality. We would say that the probability for the random variable x to be less than 2.167 hours is going to equal 0.1067 or 10.67%. Now, because of symmetry, the answer for part A would be the same. The probability of x being greater than 2 hours and 20 minutes, which is about 2.333 hours, is going to also be 0.1067. Now, you can obviously solve this using a different method by, for instance, finding the z-score for the maximum and then just using the normal cumulative distribution function from the z-score corresponding to this value up to the maximum. But I leave that to you as an exercise. So now let's focus on part C. So for part C, they want us to find the IQR of the length of the trip. So for this, we need the values for quartile 1, or 0.25 or 25%, and for quartile 3, which is 0.75 or 75%. So for this, we're going to use the function called inverse normal, which you can see that is number 3 under distributions. And the first thing we need to plug in is the area. So 0.25, then a comma. We need the mean, and we said that the mean is 2.25 hours. So 2.25, then the standard deviation, which we said is 0.0667. So we hit enter, and notice that the x value corresponding to the first quartile is 2.205. So let's write that down over here. It's going to be 2.205. So now let's find the x value. So this is the x value. Let's find the x value that corresponds to the third quartile. So then again, we go second, vars, or distributions, inverse normal, and then again, the percentage or the area, which is going to be 0.75, comma, and the other information, the mean, which is 2.25, the standard deviation, which is 0.067. We close parenthesis, hit enter, and here we get the value for x of 2.295. So this is the x value at the third quartile. So that means that the IQR is going to be the difference between these two x values. So 2.295 minus 2.205, and then we are going to get that this is approximately 0.090 of an hour. And if we multiply this by 60, we're going to get that it's approximately 5.4 minutes. So now we're going to do example 15.23, which will be the last one on this video. And it says, the age at which babies develop the ability to walk can be described by a normal distribution model. It is known that 5% of the babies learn how to walk by the age of 10 months, while 25% need more than 13 months. Find the mean and the standard deviation of the distribution. So, in this case, you have to be careful here with the wording of the problem. To clarify this, I'm going to show you a graph representing the situation. So notice that this area on the left-hand side is the 10 months that 5% of the babies require to learn how to walk. And the 25% is over the 13 months. So notice that if we look at this backwards, this is going to be 75%. So in other words, 75% of the babies need at least 13 months. So let's go to the GDC, and we're going to use the inverse norm. So here we need to find out for 5%, and we're going to standardize. So we're going to find the z value or the z-score for 5%. So this would be 0.05, and the mean is going to be 0, and the standard deviation is going to be 1. So there we get the z-score for 5%. So we're going to write it over here. Notice that it's minus 1.64, let's round it to 5. So now we do the same, but for 75%. So option 3, and this is going to be 0.75. And then again, the mean is 0, and the standard deviation is 1. So here we have that the z-score is going to be 0.674. Okay, so there are several ways to do this, but notice that this period of 3 months difference corresponds to the difference between these two z-scores, right? Remember that the z-score represents the number of standard deviations from the mean. So if you have negative 1.645 standard deviations at 10 months and 0.674 standard deviations at 13 months, then that means that the difference between them, so notice that if we go 0.674 minus negative 1.645, we're going to get 2.319, and these are standard deviations. And this is in a 3-month period, so this equals 3. We're going to get that the standard deviation is equal to 1.294. And then all we have to do is use the formula for the z-score, because we know that the z-score is equal to x minus the mean divided by the standard deviation. And we can just plug in either one of these. So let's plug in the positive one just for the sake of comfort, right? So let's say that this is equal to 13 minus mu, which we need to find as well, divided by the standard deviation, which is 1.294, and this z-score is equal to 0.674. And then from here, we're going to get that the mean is equal to 12.128.